yet. I gave 2 tests last Thursday, and I graded my other class first, but I will definitely have them back for you by Thursday. All right, today we're going to switch gears a little bit from where we've been going thus far in this course. Up till now, I've been looking at low-level vision, the structure of the visual system, how cells early on in the visual system respond to light. We've talked about perceptual organization and attention. And notice in all of those things that there is no meaning that enters into the story. So one of the main issues of this course that we're going to deal with from now until the end is the idea that we see the structure of the environment. The structure of the environment gets transformed into a pattern of light on the back of the eye. And based on the pattern of light in the back of the eye, we're able to perceive the environmental structure. All right, so I look out at the class, I see all men in this row, and I see mostly women in this row. All right, so these are examples about things that I can determine from the light that's hitting my eye. And so the problem that we're going to try and face, which turns out to be a really hard problem, is how are we able to make those judgments? Right? If you think about it, a pattern of light doesn't bear any resemblance to a thing in the world. Right? It's just light. And so how do we go from one to the other? Now, this is one of the foundational problems of visual perception. It's one of the foundational problems of computer vision. People have been studying this for well over 50 years in many, many fields, in mathematics, in physics, in computer science, in psychology, all trying to work on this same issue from different perspectives. Now, what I want to do in today's lecture is to focus on this top line right here, the structure of the environment. And in particular, I want to focus on how it is that we describe that structure. All right? How do we describe the structure of the environment? Now, it turns out that in mathematics, people have been doing this for thousands of years. All right? The origins of geometry, so geometry is the mathematics that allows us to do this, go back to hundreds of years BC. And what I'm going to do today is I'm going to give you a crash course in the history of geometry and how it's changed. Now, how many of you took geometry in, I presume, middle school? Is that when you take it? Anybody take it in high school? Anybody not take it at all? All right, so you've all had some geometry, and unfortunately, that experience you had in middle school when you learned the geometry that you learned, I promise you, is going to set you back and make it harder to understand this course if you hadn't taken it. All right, because we'll see that there are alternatives to what you learned that are probably much more relevant to human perception. But let me build up to that as we go along here. So let's talk about the beginning. Geometry was created out of necessity by the ancient Egyptians. And one of the problems they faced is that the pharaoh would tax farmers for the amount of land that they farmed. But they're farming along the Nile River, and the Nile River floods from time to time. So suppose you're a farmer and half your land gets flooded, and Pharaoh says, all right, I'm taxing you for your land. You say, wait a second, you're taxing me for all the land when only half of it's usable? That's not fair. And so the farmers would complain, and so gradually, by necessity, they worked out ways that they could calculate how much farmable land was left after the flooding. And so, again, a lot of the origins of this stuff came from practical necessity. Now, as we'll see, when geometry starts to become more and more abstract, we'll lose a little of that contact with the world, but not completely. Now, there are lots of other cultures that would train with the Egyptian mathematicians to learn what they had, because this is valuable knowledge, and particularly the Greeks were interested in this. And one of the early Greek geometers was a guy by the name of Thales. Right? This is 2,600, 700 years ago, right? We're going way back in antiquity. And Thales was said to have learned from the Egyptians and the Babylonians, and he brought his findings to the Greek Empire. And he's credited with 5 theorems, and some of them, all of them, you learned when you were in middle school. So a circle is bisected by the diameter. Angles of a triangle opposite 2 sides of equal length are equal. Opposite angles formed by intersecting straight lines are equal, so that angle and that angle are the same. Angle inscribed in a semicircle is a right angle, this one here. Triangle is determined if its base and 2 angles at the base are given. It's the angle side angle triangle congruence theorem, right? Now again, this is all the stuff you learned in middle school, and of course, it must be true or they wouldn't have taught it to you in middle school. Through much of human history, this was, right, if you challenged any of this stuff, you would probably be put to death. Remember, Galileo almost died because he suggested, albeit indirectly, that the Earth rotated around the sun rather than vice versa. And he came within a hair of being executed for that apostasy. The other thing you learned in middle school was the Pythagorean theorem. A squared plus b squared equals c squared. It's not clear that Pythagoras himself is the guy who originated this theorem. He was a head of a cult called the Pythagorean Brotherhood. And it's quite possible that Pythagoras did not create the theorem, but he got credit for it because he was the head of the group that was working on this. Now that brings us to Euclid. So Euclid wrote a book called The Elements in about right around the time of Christ. And it's arguably the most successful book ever written, perhaps other than the Bible. So it has almost 2,000, over 1,000 editions of this book. And for thousands of years, this was an essential part of the curriculum in university education until the 20th century when they started teaching it in high school or middle school. All right, so this is the geometry that you learned when you were in school goes back a couple thousand years. Now, just to give you a sense of, it's not clear what Euclid contributed and what he compiled. So the purpose of the Elements was to put together all the mathematical knowledge that was available at the time. Now, it's unquestionable that Euclid proved some theorems on his own, but he was also adopting stuff from other people and compiling it within this book. So this was a compendium of knowledge about geometry at that time. And if you all recall from back in middle school, it starts with a bunch of definitions. So a straight line is the shortest path between 2 points. Anybody know another name for that? The shortest path between 2 points? I'm sorry?
The bird thing?
I still didn't hear you.
The bird, like the bird's crow thing.
The way the crow flies.
Yes, thank you.
What did you say?
The way the crow flies.
Oh, the way the crow flies. Actually, I don't know if a crow flies in a straight line. That's a good question. We'll see. It's a tricky question to answer, but I'll get to that in a little bit. 2 lines are parallel if they never meet. Okay, these are just definitions. Now, the other thing that Euclid did is he started out with 5 basic axioms, which were the basis of his geometry, some of which were more obvious than others. Now, again, one of the amazing things about Euclid is this is the first attempt in history to really systematize mathematics, right? Where you start with a set of axioms, you prove theorems, and everything ties together. Euclid was the first guy to do this. So just the way mathematicians think, right, was initially started by him. So here are the basic axioms. I'm sure you all know them. A straight line can be drawn by joining any 2 points. So any 2 points form a line. Like so. Axiom 2. Any straight line segment can be extended indefinitely in a straight line. Like so. Given any straight line segment, a circle can be drawn by having the segment as a radius and one endpoint as the center. So we trace it out like that. Axiom 4, all right angles are congruent with each other. Again, all this is pretty obvious stuff. But that gets us to axiom number 5, which goes something like, at least at Euclid's time, goes something like this. If a straight line n intersects 2 straight lines L and M, and if the interior angles on one side of n add up to less than 180 degrees, then the lines L and M intersect on that side. That sounds a lot less intuitive, doesn't it, than a line is defined by the distance between 2 points? This is not obvious at all. I venture to say none of you have ever seen that definition of the fifth postulate because it was changed hundreds of years later. This is more like what you would have learned in middle school. For a given line L and a point P not on the line, there is a unique line through P that is parallel to L. All right, now all along, even Euclid recognized that this particular axiom seems different from the others. All the others just seem patently obvious. But the parallel postulate, not so much. And for thousands of years after Euclid, people were thinking, can we get rid of this postulate? Can we maybe prove it as a theorem based on the other postulates? Do we really need this one? Well, it turns out it carries a lot of weight in Euclidean geometry because you need it. From axiom 5, we deduce that the angles in a triangle add up to 180 degrees. This axiom is also necessary to prove the Pythagorean theorem. All right, so that parallel postulate's doing a lot of work, but it certainly doesn't seem obvious. As I said, people are not comfortable with axiom 5, including Euclid himself, and they worry that there's somehow an infinity lurking in that statement. To check if 2 lines were parallel, you had to look infinitely far along to see if they ever met. Now, you know, we don't worry about infinity so much now, but back in the day, they were real suspect creatures. Actually, there was a time when people argued whether negative numbers made any sense or not, you know, much less imaginary numbers. But anyway, infinities are not a good thing. They mostly dealt only with integers, and you know they were happy with integers. There's a study that the Greek who proved that the square root of 2 is irrational, that the brothers in his brotherhood drowned him to death because that was such a horrible result. But so for example, could this axiom be deduced from earlier, simpler axioms? So one way they try to do that is to construct a line parallel to a given line by joining all the points on the same side of L at a certain distance. So you do something like that. But there's a problem with this, and the problem with this is how do you know that the thing that you constructed is a straight line? Right? You can construct this thing, but how do you know it's a straight line? You have to somehow prove that. So ever since Euclid, people have tried to prove the existence and uniqueness of parallel lines. They all failed. But it was impossible to prove that axiom 5 was true. Could it therefore be possible to find a situation in which it is false? Now, even back in ancient times, there was one situation where they knew it was false. They ignored the situation. And it has to do with the geometry on the Earth at a big scale. Funny story about this, the spherical geometry used to be taught in my dad, when he was in high school, and I'm guessing the 1940s, was required to take a course in spherical geometry. Any ideas why this might be a relevant course to have, why this would be important, not only now but in ancient times? Why might you need to know spherical geometry? Yeah.
For traveling on the Earth?
For traveling on the Earth. If you're navigating the globe, well, suppose you're a sailor, right? You're out in the middle of the ocean and you're trying to find your way around. You need to know spherical geometry to do that. You know, now we got GPS. Don't have to know all that stuff as much. I had a story. I had a problem one time that dealt with spherical trigonometry. And this was before the internet. I know you can't even imagine such a thing, but I actually had to go to the library and I found a book on spherical trigonometry. It's exactly what I wanted to solve the problem I was going to solve. And as I was checking it out, I looked in the back, and I was the first person who'd taken that book out since the 1940s. Right? Not a popular field of study, but in any event, even the ancients knew about this. So let's see how, what is a straight line on Earth? Anybody want to venture a guess? Is it as the crow flies?
I have no idea.
Is it as the plane flies? Yes. And why they fly the shortest path? Because they use the least amount of fuel. So there's a name for the shortest path on a surface, and it's called a geodesic. And on a sphere, the geodesic is always a great circle. So the shortest path on a sphere is always a circle that cuts the sphere in half. So the circle has the same center as the sphere does. All right, so if you define a line as the shortest distance between 2 points, then a great circle is a line on a sphere. Now let's test some of Euclid's axioms. Can you extend a line indefinitely? You're shaking your head, why not?
It'll run into itself.
Oh, if you write over itself maybe, but you know, you get to the starting point again. So you can't really extend a line indefinitely. So that axiom doesn't apply. Are there any parallel lines on a sphere? Remember, a straight line is a great circle that cuts a sphere in half. Well, it turns out all those circles intersect each other twice. Right? So a sphere doesn't have any parallel lines, and you can't extend a line indefinitely. So it's not fitting within Euclid's framework very well. So here we have a great circle, and this is a small circle, but that's not a straight line because it's not the shortest distance between the points on that line. So now we get that as a plane fly. So if you take a map of the Earth, right, and you say Columbus, Ohio, and you want to go to Paris, France, right, and you put a dot on Paris, France, and you just take a ruler and draw a straight line between them, that's not a straight line. right? The straight line is a great circle. It looks something like that or that. All right, so a straight line is not straight in the way that you think about it when you took middle school. Now, if you're only going a short distance, then that works fine. A straight line is the shortest distance between 2 points. But if you're going long distances, it doesn't work anymore. So again, as I said before, there are no parallel lines on a sphere. And that's because all great circles intersect. So no two of them can be parallel. Studying the sphere shows why our previous attempt to construct parallel lines went wrong. If we take all points that are equidistant from a great circle, right? So here's a great circle, that's a line. And we take all the points that are equidistant from that here, we end up with a small circle, but the small circle is not a straight line. So that construction that people tried to use earlier wouldn't work. It turns out that if you draw triangles on a sphere, the angles will always add up to more than 180 degrees. And the sum of the angles will increase with the size of the triangle. So if I draw a triangle on this table on a scale like this, then Euclidean geometry is applicable. But let's say you go from the North Pole down to the equator, and then you travel along the equator a quarter of the distance around it, and then back up to the North Pole. What would the sum of the angles in that triangle be?
270.
270. 90, 90, 90. All right? So we're getting some weird stuff here. So again, 90 degrees, 90 degrees, 90 degrees. Clearly that does not satisfy the Pythagorean theorem. And what's worse, the value of pi isn't the same. Who knows how you calculate pi? Where did pi come from? You know?
Yeah.
Wait, am I allowed to talk?
I know a way of it being calculated, which is Monte Carlo simulation, where you have a 1-by-1 square and you inscribe a circle in it, and it's the ratio of area of, I think that's right, it's like the ratio of the area between the circle and the square.
Spoken like a true computer scientist. So how did the Greeks determine it?
Perimeter of the circle.
I'm sorry?
The perimeter of the circle over the radius? No, over the diameter.
So what's the equation for the area of a circle?
Area of circle is
PR squared.
yeah.
Oh, I'm sorry. What's the equation for the circumference of a circle?
2PR.
Right? 2 pi r. And so how would you calculate pi? You measure the circumference of the circle, and you divide it by the ratio, by the radius. Right? Now, if you do that on a sphere, how many of you know pi to some number of digits? How far can you do it?
3.14.
Come on, my computer scientist can do better than that.
Got it right in front of me, it's cheating.
Oh, that's cheating.
And that's as far as I know. 1.14159.2.
I can do 3.1415927. That's as far as I can get. There was a time when I knew the reciprocal of it also, but not anymore. So it turns out if you do this on a sphere, depending on where you draw the circle, you get a different value of pi. So pi changes from circle to circle. So geometry in a sphere clearly violates Euclid's fifth axiom, but it also doesn't satisfy axiom 2 and 3. That is, straight lines cannot be extended indefinitely and circles cannot be drawn with any radius. So people just sort of ignored this. Euclidean geometry was so ingrained that, yeah, it doesn't fit here, but we're not going to worry about it. But we still want to know about spherical geometry because it helps us navigate the globe, right? There's no region that historically people have to be consistent with one another. And again, I have to stress the point that through much of Western civilization, Euclidean geometry was something given by God. To challenge that, you'd really be risking your life. That's a much bigger deal than arguing that the Earth spins around the sun. So people would, even if they could prove that Euclidean geometry wasn't the be-all or the end-all, they would be reluctant to say so publicly. So now the question is, what if axiom 5 were not true, as suggested by the spherical case? Is there some way that you could satisfy Euclid's axioms 1 and 4 and only contradict axiom 5? And for a long time, people didn't even bother to think about it. They just took these axioms as if they're God-given sacrosanct things. And when they did try, they were usually unable to overcome the force of their intuition. Now, this is what I want to warn you about in this course, all right? I'm giving you this lecture for a reason. And the reason is that Euclidean geometry is so ingrained in your mind that when we see situations where it's not the appropriate geometry to use, it's going to be really hard for you to put your arms around it. All right, and that's why I'm trying to develop this early on before we go down that path. So one example of this was in 1733, a guy by the name of Sakaki. He tried to establish the validity of axiom 5 by means of a reductio ad absurdum proof. How many of you have heard that term before? Reductio ad absurdum. All right, so the basic logic of it goes something like this. I assume something is false, like the parallel postulate. And then from that, I derive some state of affairs that is obviously not true. Right, so by assuming something is false, I get to a result which I know to be untrue. That's what's called reductio ad absurdum. And that's a valid form of proof in mathematics. So what Sakaki tried to do that, and when he did it, he couldn't find something that was obviously false, which might suggest, well, maybe you don't need the parallel postulate. But then he said, never mind. It's repugnant to the nature of straight lines to assume that the parallel postulate is not true. So he just gave up on his enterprise. And that leads to the main story that I want to tell today about 4 very famous mathematicians. These are people who really did think about alternatives to Euclidean geometry and were willing to, in some cases, actually publish it. And so the main players of this story are Carl Friedrich Gauss. Some people argued the greatest mathematician who ever lived. Farkas Bolyai, Janusz Bolyai, his son, and Nikolai Ivanovich Lobachevsky. All right, I'm sure you've all heard of Gauss. Any of you heard of any of these 3 characters? None of you. All right, well, you're going to hear an interesting story today. Here we have Gauss. He was born in Germany. He's a child prodigy, wrote his magnum opus at the age of 21. For some reason, mathematicians do their best work at a really young age. And they peter out with age a lot earlier than, say, psychologists do. But then one could argue that the contribution of psychologists is not as great as mathematicians. But he often made discoveries years before his contemporaries. And here's a key that will come into play later. He often didn't publish because he was so much of a perfectionist, right? So a lot of Gauss's discoveries weren't known until after he died and people went through his notebooks. And that'll be important in the story that I'm going to tell you here. So Gauss discussed the theory of parallels with his friend Farkas Bolyai, who's a Hungarian mathematician. And Bolyai spent much of his life trying to prove axiom 5 from the other axioms. I mean, he really had a compulsion about this. And Farkas, in turn, taught his son Janos about the theory of parallels, but warned him, do not waste 1 hour's time on that problem. I know this way to the very end. I have traversed this bottomless night, which extinguished all light and joy in my life. It can deprive you of your leisure, your health, your peace of mind, and your entire happiness. I turned back when I saw that no man can reach the bottom of this night. I turned back unconsoled, pitying myself and all mankind. Learn from my example. Now, what do you do when your dad tells you something like that?
I would not do that problem.
Well, Bolyai did. And when his father found out about it, he wrote him the following. For God's sakes, please give it up. Fear it no less than the sensual passion. Now you really got to start to wonder about the father. Because it too may take up all your time and deprive you of your health, peace of mind, and happiness in life. And Janos ignored him. So this is Janos Bolyai, born in Transylvania. Could speak 9 languages and play the violin. Mastered calculus apparently by the age of 13. And he became obsessed with the parallel postulate. And lo and behold, he was able to prove that you can have a completely consistent geometry where the parallel postulate is false. Big friggin' deal, right? Again, this is sacrosanct information for like 2,000 years. I won't say it the way Joe Biden said it. So in 1823, he wrote to his father saying, I've discovered things so wonderful that I was astounded. Out of nothing, I have created a strange new world. And his work was published in an appendix to a book written by his father. Now, right, the father, Bolyai, is friends with Gauss. Right? His son writes him and said, you know this thing you worked on all your life and failed? Well, I did it. Now, there are 2 possible reactions. What would a typical dad do when faced with this situation? What would your dad do?
I'd probably be pretty impressed, and I guess I don't know.
A good dad would do that. How about a bad dad?
Bad dad? Maybe jealous.
He might curse you, say you didn't do it right, you know, you didn't pay attention to me. Well, apparently Farkas Bolyai was a good dad. And he was so proud of his work son that what would he likely do? Right? The big dog mathematician at the time was Gauss and a personal friend of Farkas Bolyai. So if you're Farkas and your son shows you this amazing discovery, what you going to do?
Brag about it to Gauss.
Brag about it to Gauss. And what do you think Gauss said?
It's pretty cool.
Gauss said, yeah, I've known that for 20 years. Which apparently he did, but he didn't tell anybody. Now, actually, in some letters, Gauss is very complimentary about Bolyai. But, so Bolyai was excited. He then receives the reply from Gauss when he tells him about it. To praise it would be an amount to praising myself, for the entire content of the work coincides almost exactly with my own meditations, which have occupied my mind for the past 30 to 35 years. Now, it's true. They found in Gauss's notes after he died that he'd worked on this stuff. But he didn't tell anybody. Maybe because he thought it would be too controversial. Maybe he didn't think he had the story right. But he was sufficiently a jerk to say, okay, you did this independently, but I'm not going to give you any knowledge for it because I thought of it first. Scientists can be real schmucks. I know of instances like this. I won't go into them, but. So that brings us to Nicholas Lovichevsky. He was born in Russia, said to have 18 children, was the first person to officially publish non-Euclidean geometry. Some people have accused him of stealing from Gauss, but there's no evidence for this. So what Gauss and Bolyai invented is what's sometimes referred to as hyperbolic geometry. So this is the geometry where there are no parallel lines. In fact, all parallel lines, I'm sorry, there are an infinite number of parallel lines. All parallel lines diverge from one another. So it's not just one line through a point that's parallel to another line. There are an infinity of them. The angles and triangles add up to less than 180 degrees, and pi is always greater than 3.14159. So this is a special kind of non-Euclidean geometry called hyperbolic geometry. Now, there's another kind, so we can violate the parallel postulate by saying, all right, so what's a parallel postulate? Through any point P and any line L, there's a single line through P that's parallel to L. So in hyperbolic geometry, we say, no, that's not the case. Through any, there are an infinity of lines through P that are parallel to L. And we could also invent another kind of geometry called elliptic geometry, where there are no lines through P that are parallel to L. And this geometry was invented by another great mathematician, a guy by the name of Bernard Riemann. Now, Riemann was Gauss's last student. It's probably the only reason Gauss allowed him to work on this problem. And when Gauss finally retired, Riemann took his chair. Now, you got to know in Europe, especially during this time, unlike the United States, so in our department here in psychology, we probably have 30 full professors. In the Department of Germany, they'd usually have one, maybe two. All right, so a professor in Europe, especially back then, was a much bigger deal than it is now. And they have a custom that they still do today. It's a wonderful custom. I wish we did it. So when you're appointed to a professorship, again, much more prestigious than a professorship here, the tradition is you get dressed up in academic gowns and you give a speech to all the professors in the whole university. All right? Now, typically, you would bring out your best stuff because this is a big deal rite of passage when you become a professor. And so what Gauss did is he introduced, outlined a coherent geometry of many different kinds of space whose geometries are defined by how they are curved. How many of you have heard of Riemannian geometry before? What do you know about it?
I know some, like I don't know how you say it. I know I studied that.
Yeah, so when Riemann did this, he also introduced a notation called tensor calculus. There probably, the people who could understand this at the time, you could count on one hand. But there was one guy who could understand it and really make use of it. Any idea who that guy is? Albert Einstein. All right, so this is the underlying mathematics behind Einstein's theory of general relativity. Now remember, when Einstein came out with it, most of the physicists of his time couldn't understand a word of this. And in fact, they thought the idea of physicists doing mathematics was sort of a sacrilege. They should all be running experiments. But Einstein really changed that. So in any event, at his inaugural lecture, Riemann talked about many different kinds of space. And in elliptic geometry, there are no lines parallel to a given line through a given point. In fact, all straight lines intersect at 2 points. Angles and triangles add up to more than 180 degrees, and pi is always less than 3.14159. So in Euclidean geometry, there's a single line parallel to a given line through a particular point. Sum of the angles is always equal to 180 degrees, and the Pythagorean theorem is satisfied. In elliptic geometry, there are no parallel lines. The sum of the angles of any triangle is always greater than 180 degrees. Pythagorean theorem is violated, and similarly for hyperbolic geometry. Now, the way to visualize this is as follows. You can think of elliptical space as the geometry of a sphere, Euclidean space as the geometry of a plane, and hyperbolic space as the geometry of a saddle, like the crook of my elbow. All right, so depending on the curvature of the space that you're concerned about, these different geometries will come into play. In 1917, Albert Einstein published his theory of general relativity. This would not have been possible without non-Euclidean geometry. Relativity tells us that space-time gets curved by matter, and this is what causes the effect of gravity, and light gets bent and time slows down in the gravitational influence of large objects. Any of you seen that recent movie? I forget the name of it. What's that? Yeah, the guy goes through a black hole and then comes back, and he's a young guy and his daughter's about to die of old age. It's a pretty accurate depiction of Einstein's theory of relativity, general relativity. So at the time, the big prediction of this was that light gets bent by gravitational fields. And so the real test of it was an experiment that was done by Eddington, where they showed that light bends around the planet Mercury, which was very controversial. Eddington was a British physicist who was mathematically pretty skilled. And keep in mind that what Einstein's theory was replacing was Newton's theory. So the Brits were not too happy about having that occur. But Eddington apparently wanted the truth and didn't want to just support his countrymen for our understanding of gravity. All right, so now we'll get into the weird. What's the geometry of visual space? So imagine a triangle. How many angles? What's the sum of the angles? That's the question you'd want to ask. Now notice this is a hard problem because we know what the answer is, right? Sum of the angles is 180 degrees. So we need to come up with more subtle ways of testing it. And one way of doing that is an experiment done by one of my old-time collaborators, Jan Kunderink at University of Utrecht. The Netherlands is an interesting country because the people who study visual perception and motor control are all trained in physics rather than psychology. So they have the formal background to do a lot of this stuff, whereas psychologists typically don't. So this is a simple task. You have a radio-controlled car, and you have two posts, and you're told to stick this bar that you can control so that it exactly bisects these two posts. Everybody clear on the task? So if you think of the task, right, here's your bar. Which way would you move it? This way or that way? To create a bisection. Move it toward the observer to the right, and you'd stop when you get right there. All right? That's what a subject ought to do if they're correctly doing the bisection. Here's what they actually do. Right? So that the sum of the angles is less than 180 degrees. So this suggests that visual space is in fact a hyperbolic space, not a Euclidean space. Now again, I'm reluctant to teach this in a class because of course space is Euclidean, right? But what we're talking about here is your internal representation of space doesn't have to be exactly like what physical reality is. Now, it turns out that once Lobachevsky, Bolyai, Riemann started introducing alternative geometries, again, this was very radical stuff, right? We'd gone from Euclidean geometry is perfect, it's given to us by God, and now all of a sudden there are these two upstart alternatives that crop up. And then people started noticing, hey, you know, there's a bunch of other geometries as well that we haven't really thought of as geometries, but they've been around for a long time. So one of them is projective geometry. It was first considered by Pappus of Alexandria in 200 AD. We'll talk about Brunelleschi a little later in the geometry of linear perspective, very important in the history of art. There's topology. Any of you heard of topology before? So it was started by one of the other great mathematicians, Leonard Euler, in 1735, invented graph theory. And so the problem he was trying to solve is abstract, blah, 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 blah. So basically, can you cross each bridge in the city of Königsberg once, and only once, but cross all 7 bridges? And Euler proved that you can in fact do this. And in the process, he invented this thing called graph theory that we still use today. And that brings us to Felix Klein, is another German mathematician who was appointed as professor of mathematics at the Erlanger University, which is another city in Germany. And he was appointed professor, so what do you do when you're promoted professor? You give an inaugural speech, you get dressed up in academic robes, you trot out your best stuff. And Klein then revolutionized geometry ever since, right? So we started out with just Euclidean geometry, and then we had elliptic and hyperbolic geometry, and then we got projective geometry, and then we've got topology, and things like affine geometry and conformal geometry. These geometries are springing up like weeds, which makes mathematicians really uncomfortable, right? So within 1 century, they've gone to there's this one thing given by God, to these things are, you know, they're like weeds. And there must be some way of tying them all together. And that's what Klein gave us, was to show us how to do that. So Klein described geometry as a set of points and a set of transformation defined on those points that preserve some properties but not others. Now, I don't want to go into the gory details of this. Oh, by the way, from this it's possible to prove axioms as theorems rather than assume that they're true. Moreover, it's possible to relate different geometries to one another based on the invariant properties they share in common. So to try and give you a sense of this, let's think of what happens when you change an object. Can I borrow your notebook? All right. So let's say I take the notebook and I do this to it, or I do this to it, or I move it in space like so. What have I changed about this notebook? What's that? You've changed its position in space. You've changed its orientation in space. What haven't I changed? How about the lengths of the sides of the edges of the paper? Have I changed that? All right, so some things changed, the position. Some things didn't change, the length of the edges on the paper. All right, this is the core insight of Kleinian geometry. Now let's suppose that I do, so this is an example of a Euclidean transformation, is one that preserves length and angles. So if you take this object right here and you transform it into that, The orientation and position have changed, but all the lengths and angles are the same. So Euclidean transformation is one that preserves all lengths and angles. You can also change the size of the thing to a similarity transformation, and that changes the lengths, but it doesn't change the angles. Or I could stretch it like so. What's preserved here? So what changes from this to this? Let's pick on you. What's different about this shape than that shape?
What's different? Angles are different.
Are the lengths different?
Lengths are different.
What's similar?
Still a parallelogram.
That's about it.
Okay, yeah.
But that's an important property. Okay? So transformations that preserve parallelism are called affine transformations. Transformations that preserve angles but not lengths are called similarity transformations. Transformations that preserve lengths and angles and parallelism, all those things, are called Euclidean or rigid transformations. How about this one? How are these two different? Let's pick on you this time. What's different between these two? The lengths of the sides are different. The angles are different. What's the same? Be careful. Anybody see something that's the same in those two figures? Don't think Euclidean geometry. Area is a good guess, but you can't tell that immediately. So what hasn't changed is the fact that the sides are all straight lines. The hint for that is here. Okay, I'll give you another crack. What's the same between these two objects?
The triangle angles.
They have the same number of holes. All right? So we can get pretty abstract here. Now, I'm going to show you an experiment a little bit later to try and convince you that we are much more sensitive to this than we are to that. So those Euclidean properties that we take for granted that you learned in middle school, those turn out to be really hard for us to see. All right? The really easy stuff for us to see is this. Or if we now destroy the topology, we create what's called a catastrophe. So topology is sort of like what's sometimes referred to as a rubber sheet transformation, right? You can distort things willy-nilly, but you preserve adjacency relationships. You preserve the number of edges, you preserve the number of holes, the number of vertices. There's a whole area of mathematics that's based around that. So that's listed off here. Euclidean transformations preserve lengths and angles. Similarity transformations preserve angles and length ratios. Affine transformations preserve parallelism and the length ratios of parallel lines. Projective transformations preserve collinearity. There's another thing called a cross ratio I won't bother to define for you. Topological transformations preserve patterns of nodes and edges and the number of holes. Now, very interesting paper. I have a good friend in China. His name is Lin Chen. And Lin has an interesting background. He grew up, started college when they had the Cultural Revolution. Anybody know what the Cultural Revolution was in China? So it was a period before Mao died, but he was sort of out of power. And his wife and another guy whose name I forget became really negative about intellectuals. And so they closed down the universities and made all the university professors and students go on work farms. And this period was called the Cultural Revolution. And so Lin Chen was initially sent to work in an iron ore processing facility. And apparently he was very good at this and was, after a few years, was running the show. But then when they allowed the universities to reopen, he requested to be able to go back to the university. He had to get permission from his boss in order to do this. And he was originally trained as a biophysicist, but when he came back, he became much more interested in psychology, and particularly perception. But it turns out they didn't have any textbooks in it. They burned all the books. The older professors, most of them weren't allowed to come back. And so he's this young kid, trained in biophysics, but wants to study perception and uses some of the tools he learned in biophysics to do this. And he came up with this interesting hypothesis that in fact what we're primarily sensitive to is topology. And so here's a demonstration that he used to argue that. This is, remember we talked about pop-out before. So the basic idea here is that you see a pattern like this and you have a lever and you have to move it to the location where the object is different from the others. So which one stands out as different? Let's pick on you this time. This one right here? Lower right.
Yeah, lower right.
And which one's different here? And which one's different here? All right, now it turns out that these are not equally difficult. So if you look at the reaction time for doing that, this one, subjects make that response in under a second. If you look at this one, it's closer to 2 seconds, and this one, it's over 2 seconds with higher errors. Now notice the thing they're detecting is exactly the same in every case. What you've done is you've just taken one line and reversed its orientation from up to the right to down and to the right. That's what makes it different here. That's what makes it different here. The reason why this pops out is in this case, the element that you're trying to detect has a different topology than the other elements in the display. Right? So what Chen is arguing is that topology is the most basic property that we are sensitive to. Now, I recently did a study in my lab where we did a similar demo. And there are two possible, so this involves a task called a match to standard task. You have a standard object and then you get two foils and you have to, you get two test objects and you have to decide which of the test objects is the same as the standard. And these are the two possible standards. And so here would be an example of different transformations. So this one, we just compressed the sides a little bit. In this one, we skewed the sides a little bit. In this one, we added a bump. And this one, we added a hole. Now, which of these you think is the easiest to detect? You say the hole? Which one do you think is the hardest to detect? The stretch? Do you all agree? This one looks easier to detect than that, and these two are somewhere in between. Notice here you're detecting a topological property. Here you're detecting a Euclidean property. Here you're detecting an affine property. Here you're detecting a projective property. Now, in order to compare these things, we need to have a metric of some sort to describe the nature of the shape change. We looked at a lot of them. I'll just tell you about one. This is called a Hausdorff metric, which is the displacement of the maximally displaced point. And that's the reason we use two different standards, because by the Hausdorff metric, all three of these have the same amount of change. But as we'll see, that's not how it worked out for human perception. So here's what a trial looks like. You see a fixation point. The standard appears. Then the test appears. And another test appears. Which one was different? The second one. Let's try another trial. Oh, I don't have another trial. I gave you the easy case. If we look at how much displacement is necessary, it turns out that the smallest displacements are detectable in the topological condition. In the bump condition, you're a little worse. In the skew condition, you're a little worse still. And in the stretch condition, you're much worse. All right? So what this is showing is in terms of our sensitivity, there's this hierarchy of relations. We're really good at seeing the topological properties. We're not quite as good in the projective properties, not quite as good in the affine properties, and terrible at the Euclidean properties. Now also, if we measure these things in terms of how much, at threshold, how much distortion we were actually making, it turns out that the stretch transformation, so this is the correlation based on simple cell responses. It turns out if you think about that the cells in the cortex are detecting this change, they predict the opposite of the result. So they predict that the Euclidean property should be the easiest and the topological property should be the hardest. All right, so we're doing some abstract stuff here that is definitely not consistent with what you learned in elementary geometry. Now, I realize I've tossed out a lot of novel stuff to you, but you have to trust me that this basic idea of sensitivity to different aspects of structure depending upon their stability is one that we're going to come back to over and over and over again, especially in the next 2 lectures. So let's just test you a little bit. Which line is longer, AB or CD? You all say CD? And what kind of property am I testing you when I ask you that question? Euclidean, right? I'm asking you to tell me about relative lengths. Is alpha parallel to delta? Yes or no?
Yes.
What property am I asking you about there? Right? Affine geometry is the one that is about parallelism. If I ask you, are A and C on the same face, what's the answer? What kind of geometry am I talking about there? That's topology. All right? And I think you will agree that judging that these things are on different faces is a hell of a lot easier than deciding is this length longer than that length. All right? So judging lengths is really hard. Judging topology is pretty easy. Judging things about parallelism is sort of intermediate. And there's a good reason for that, of why we should be sensitive to those properties, because if you think, when objects are projected on the retina, are lengths preserved when objects are projected on the retina? Right? So look at my arm. Is this part of my arm longer in the projection than this part is?
Yes.
Yeah, it is. All right, you only see a small visual angle of this. You see a much bigger visual angle of that. The lengths of things change in optical projection, right? And so, for example, the length of my arm is pretty small to you right now, but if I rotate, it gets much longer. But topology doesn't change. Parallelism doesn't change. So some things are invariant when you look at objects from different points of view. And if they have properties of objects that are invariant over changes, they're really diagnostic. They're really useful things to exploit. And we'll see that the brain takes advantage of that. In particular, next time I'll give you a much less, I promise, dense lecture than this one, where we'll explore some of these geometric ideas within the context of visual illusions. So I realize I'm not expecting you to have this completely mastered now, but as we see more and more and more examples of this stuff as we go forward, I want you to recognize that it's the distinction between these different kinds of object properties that's going to turn out to be an important thing we need to know in order to understand how we interpret the visual environment. So we're very good at judging things that are stable under change and not so good at judging things that are not stable under change. So hopefully you've learned a bit of geometry. And again, I don't expect you to have it mastered quite yet, but one of my goals for this course is to give you enough examples of this stuff so that in 3 or 4 weeks from now, when I ask you about some particular kind of property, you go, oh, that's projective, oh, that's affine. All right, that's my goal. We'll see if I can achieve it. So I'll let you go here. And as I said, I will turn back the test on Thursday.